All right, as we wrap up section 1, we've last time defined stress and strain, and earlier we've defined tensor transformation, so now we're going to kind of combine those two together here. And let's start out by doing transformations of strain. So here's our definition of a second order tensor transformation. Notice there are two lambdas there. Excuse me. And the definition of lambda is the cosine of the angle between xi prime and xj axes. And so we found that for a rotation about the x3 axis. We did that earlier. And so we can actually write them as a matrix, our lambda terms. And a little bit of shorthand here, instead of writing out cosine and sine of theta every time, we're going to let m be the cosine and n be the sine. And we'll use that nomenclature throughout the course. So let's start out by trying to find the epsilon 1 prime. So we're looking at the normal strain now in the 1 prime axis. So applying our definition of the second order tensor transformation rotations here, you can see that the first subscript on the two lambdas both match the subscripts of the term we're trying to find. So these will both be just constants 1 and 1. So P and Q will be summed over P equals 1, 2, and 3, and Q equals 1, 2, and 3. So there'll be 9 terms here. And so let's look at the first 3. If we let, in this case, P be 1 all the way across, and Q be 1, 2, and 3, and so epsilon PQ becomes 1, 1, 1, 2, and 1, 3. The next 3 terms will let P be 2 all the way across, and Q goes from 1 to 2 to 3, and finally now with P equals 3 and Q equals 1, 2, and 3. So you can see kind of a matrix effect as we're doing this. Now if we plug in those values of lambda that we identified earlier, then that first row becomes the cosine squared, or m squared, times epsilon 1, 1, plus lambda 1, 1 times lambda 1, 2 is m times n. And finally, wherever we have a 1, 3 or a 2, 3, we know we're going to have a 0. So 0 for this term. The second row, you can again see lambda 1, 2 times lambda 1, 1 is going to be sine times cosine. Lambda 1, 2 times lambda 1, 2 is the sine squared, n squared, and again 0 for the last term. Going across the bottom, we have 0, 0, and 0. So putting that all together and remembering that epsilon ij is equal to epsilon ji, so I can combine the epsilon 1, 2 and the epsilon 2, 1 terms together, and I come up with the final form here. The cosine squared times epsilon 1, 1 plus the sine squared times epsilon 2, 2 plus 2 times this cosine times the sine times epsilon 1, 2. Okay, we'll do a couple more of these. Let's do epsilon prime 1, 2. So again, the first subscript of the lambdas, the first one's 1, the second one's 2. So expanding all that out, again, just like we did last time, the first row represents P equals 1, the second row is P equals 2, the third row is P equals 3. The first column is Q equals 1, the second column is Q equals 2, third column is Q equals 3. And we put in our values for the lambda terms as such. Remember again that we can combine the epsilon 1, 2 and epsilon 2, 1 because they are the same. And so here's our equation for epsilon 1, 2 prime. And you might just try working through these on your own to make sure you kind of get the procedure of how we're doing this. So in this case, epsilon 2, 3 prime. Putting our numbers into here, you can see you end up with a lot of zeros, and the only terms are minus n epsilon 1, 3 and plus m epsilon 2, 3. Epsilon 3, 3 prime, we're going to end up with a whole lot of zeros and only one non-zero term, and that's lambda 33 times lambda 33, which is just 1 times 1. So that makes sense that epsilon 33 prime would be the same as epsilon 33, since those two directions are the same. And we could go through a couple of similar things here to find epsilon 13 prime. And epsilon 22 prime has a similar form to epsilon 11 prime. And now, because of the fact that there are, we have these epsilon 21 being epsilon 12, and the same for the prime system, that there are only 6 independent strains instead of 9. So instead of writing these in a 3 by 3 matrix, we're going to write it as a 1 by 6 matrix. And so here's how we're going to do it. And again, we'll do a little bit of shorthand here. Normal strains are going to be epsilon 1, epsilon 2, epsilon 3. Shear strains are going to be epsilon 4, 5, and 6. So you can see how we're doing this. Epsilon 4 will be epsilon 2, 3. Epsilon 5 will be epsilon 1, 3, and epsilon 6 will be epsilon 1, 2. And again, once again, we'll let m be the cosine and n be the sine of the angle theta. And now we can write a matrix equation that has our primed values on the left, our unprimed values on the right, and a 6 by 6 matrix that transforms from one system into the other. Now for stress, we can do a similar kind of thing. And again, in mechanics of materials, you sort of did this already. You looked at a block of material and you sliced it, and what you come up with are the same as what we saw for strain. So again, we didn't show that stress is a second order tensor, but it is, and so it has the same transformations as does strain. Now our contracted notation, once again, normal stresses, what we'll call sigma 1, sigma 2, and sigma 3, and the shear stresses, sigma 4, sigma 5, and sigma 6. And of course, with strain notation, stress notation, we usually call the shear stresses taus instead of just sigmas. And so, but again, with a contracted notation, we're just going to call them sigma 4, sigma 5, and sigma 6. And so our transformations will be exactly the same as they are for strain. So both stress and strain are second order tensors. So to transform from one coordinate system into the other, we now know how to do that. We use this same 6 by 6 matrix to do so. Now just one note about the contracted notation is that when we wrote those stress-strain relation, when we write the stress-strain relations later on, what we'll find is that from mathematically we would write it like this: that there are stiffness terms, which we'll call the C terms, but to look at the possibility of all the coupling between the stress and strain terms, that would be a fourth order tensor that connects those two. Well, a fourth order tensor has 81 terms. Well, of course, a lot of those will be 0. But if we use our contracted notation to where we've only got 6 values of stress and 6 values of strains, then the C terms will only have 36. In other words, it's a 6 by 6 matrix. So that becomes a lot easier to work with than having 81 terms in there. And we're going to use that to find what a lot of those 36 terms are. Again, a lot of them are going to be 0. We'll also find out that that 6 by 6 matrix is going to be symmetric, so that simplifies things a little bit. But that's what we're going to do. Next section, we're going to use the transformation equations, and we're going to look at stress and strain in a composites local coordinate system, which we define by the fiber direction, and whatever structure we have, their global coordinate system. So we'll finally get into a little bit of composite mechanics as we begin section 2, the mechanics of a composite lamina.